Hello everybody and welcome to my flash presentation introducing the Ngeli lobe of the Mount Ayliff Complex in South Africa. The Mount Ayliff Complex is part of the Karoo Igneous Province in southern Africa. The complex consists of 5 lobes, the most famous of which being in Sizwe that hosts nickel-copper mineralization at its Waterfall Gorge deposit. The other lobes have been relatively poorly studied, and we aim to evaluate the petrogenesis and prospectivity of these poorly studied lobes. Today, I will simply introduce the second largest lobe of the complex, the Ngeli lobe, and discuss how we believe that it may have formed. So, the Ngeli lobe is approximately 800 meters thick. It consists of a basal olivine gabbronorite, a leucellite unit, a central olivine gabbronorite that coincides with a sharp transition between ultramafic to mafic rocks, a central gabbronorite, an upper olivine gabbronorite that can have up to 5% olivine, and an upper gabbronorite. Here's how those ultramafic rocks look in thin section. Olivine grains range from equant to hopper textured, and they host numerous polymineralic inclusions, such as here, that we've interpreted as melt inclusions. In addition to this, they also host fine blocky chromite grains, chains, or clusters. Coarser and more faceted chromite grains occur in the interstitial materials, and presently we are interpreting this relationship as a product of chromite synuesis during entrainment, whereby some of those chains were protected from post-cumulus ripening processes by becoming encapsulated within the undercooled olivine. Blebe, pyrrhotite, pentlandite, and chalcopyrite are present, but they're concentrated at and just a few meters below the transition between mafic and ultramafic rocks. In the upper mafic portions, we have a thick package of subophytic textured gabbronorites that sparsely contain olivine. The olivine here also have these melt inclusions and chromite inclusions, but chromite doesn't appear to occur outside of the olivine grains themselves. Lastly, at the roof of the intrusion, we also see orthopyroxene with clinopyroxene X solution lamellae, so we begin to see some features consistent with slowed cooling. Now we're looking at geochemistry through the Ngeli lobe. The lower ultramafic cumulate rocks have relatively high magnesium, iron, chromium and nickel contents, as well as low calcium and incompatible trace element contents. There is also evidence for a basal reversal where the trends are augmented by the presence of country rock xenoliths, so a combination of that and trapped liquid. At around 450 meters, we see an abrupt geochemical transition marking the switch from ultramafic to mafic rocks, and this coincides with the appearance of Blebe sulfide mineralization as identified by this sort of yellowy box here, but at present we've discovered nothing to write home about really here. The mafic rocks have relatively lower magnesium, iron and nickel contents, as well as higher calcium and an upward increasing pattern of incompatible trace element contents. Over on the right, we see that in the lower portion, olivine forsterite content sits at around 80 to 84, and this doesn't nicely correlate with nickel concentration of those olivine grains, so it appears processes such as trap liquid shift or possibly olivine sulfide interaction, particularly at the transition zone, could be responsible, and it's something that we're exploring. Now, there is an ongoing debate as to what the nature of the parent magma was. Several believe a Karoo-type doleritic magma charged with olivine was responsible. The liquid in this case has around 7 weight% magnesium. However, there are others that believe something a bit more tholeiitic was responsible, maybe with up to 14 weight% magnesium, based on observations from the chilled margina in Sizwe. We've tested a number of parent magmas and conditions, and I will summarize an alpha melt simulation that nicely reproduces our data. So firstly, using the composition of a sill present in the Sizwe footwall, we can nicely reproduce the rocks at 2 kilobar and the FMQ oxygen buffer by fractional crystallization. Wolfgang Meyer sampled this sill, and it has around 8 weight% magnesium and trace element profiles somewhat identical to that of Karoo dolerite. Using the first liquid and the first solid crystallized from that liquid, we can draw a tie line between these coexisting phases and almost perfectly reproduce the ultramafic cumulate rock units. As that liquid continues to evolve, we switch from a liquidous assemblage of olivine and spinel to one of clinopyroxene, plagioclase, and orthopyroxene, at which the coexisting solids and liquids can produce a tie line that perfectly explains the upper mafic portion of the unit. Now, this model also works for other major oxides, the trace element data, as well as the olivine compositions that we have collated. So therefore, we believe something comparable to crude dolerite with some olivine was responsible. Thank you for listening. Here are some references to key works in this area, and some preliminary conclusions is that we don't see any incisor style sulfide mineralization. We do see evidence for grain transportation, sinuesis, undercooling, and ripening. And the rocks can all be explained quite nicely by low pressure fractionation of an olivine bearing basaltic magma that we believe quite possibly is the Karoo dolerite magma. Thank you.